Calculating the Ka of a weak acid from pH. So essentially to do this, we're going to use an ice table or a rice table if you prefer, but we have one key piece of information that is going to help us, and that is that if we know the pH of our solution of acid, well, that means we're going to be able to calculate what our concentration of the hydronium ion is at equilibrium. So as always, you should write out the ionization of your weak acid. So this is our carbonic acid. So if that donates an H+, you're going to get the bicarbonate or hydrogen carbonate ion as its conjugate base. And then donating a proton to water will give you the hydronium ion, and it's that concentration of that hydronium ion at equilibrium that is going to give us our pH. So you can go ahead and make your ice table or your rice table, whatever you prefer, depends what textbook you've been learning from, right? So your reaction is going to be your concentration of your carbonic acid. We're going to leave out the water because it's a pure liquid, so it does not appear in the equilibrium constant expression. And then the concentration of our conjugate base and the concentration of our hydronium ion. And then we can fill out the table with what we know and what we're trying to find out. So reaction, initial, change in equilibrium. So we know the initial concentration of carbonic acid is 1.3 molarity, and we are starting with 0 of our bicarbonate ion and approximately 0, because, you know, auto-ionization of water, approximately 0 concentration of the hydronium ion. However, because we know the pH, well, pH is minus log of the concentration of the hydronium ion, right? So we can rearrange that. So log of H3O plus is going to be minus pH. So do 10 to the power of each side. So 10 to the power of log just gives me hydronium, and then that will be 10 to the power of minus pH on the right hand side. So our pH was 3.12. So my concentration of my hydronium ion at equilibrium, I'm going to get by doing 10 to the power of minus 3.12, and that's going to give me a number which will be my concentration of hydronium at equilibrium, which is 7.586 times 10 to the power of minus 4. I had to check the number of zeros there. So obviously, if you're doing an ice table and you didn't know the pH, so you didn't know the concentration of hydronium at equilibrium, this would be where you would stick some X's in to your ice table, right? So you say, well, okay, if my equilibrium concentration of H plus or hydronium is going to be X, then I could work backwards from that. So I'm going to end up with X being the concentration of hydronium. So then my change row has to be that over the course of the ionization, I'm forming X moles of hydronium, and I'm also forming X moles of the conjugate base. Sorry, and to do that, I'm using up, so minus X moles of that weak acid, right? So this would be how you would normally fill out your ice table. And then at equilibrium, you're just going to add down each column. So initial plus change equals equilibrium. So I'd end up with 1.3 minus X for my equilibrium concentration of my weak acid. And I just end up with X for my equilibrium concentration of my bicarbonate ion and my hydronium. But now, because I have the pH, I can actually fill in those values of X. So my concentration of hydronium at equilibrium is 7.586 times 10 to the power of minus 4. Let's try and make that look a bit prettier. There you go. So I can then just plug and chug that everywhere. So, of course, my plus X here, that's what that's going to equal. For my plus X here, that's what that's going to equal. Tidy that up a little bit. And I'm going to need much more space here than I anticipate. And of course, don't forget a minus in front of it here. So minus for this guy right here. Okay, so then I can fill out for my equilibrium concentration of my bicarbonate, and 1.3 minus by 7.586 times 10 to the minus 4 for my equilibrium concentration of my weak acid. So of course I can then go ahead and actually work out what that would be to make life easier on myself. So just as an FYI, if I calculate that, that will be 1.299. So I'll just put that in brackets there. So then, if you haven't already done so, which I didn't because I was busy talking, I should write my Ka expression for my equilibrium. So concentration of products on the top, each raised to the power of their stoichiometric coefficient, which is 1. So that's just going to be itself divided by reactants. So that's just going to be the carbonic acid, because remember, we don't count water. So now I can actually substitute in my actual equilibrium concentrations, because I actually have them, the numbers, so I can stuff those in. So that's going to be my 7.586 times 10 to the minus 4 times 7.586 times 10 to the minus 4 divided by my concentration of equilibrium of bicarbonate, sorry, carbonic acid, which shook out to be 1.299. So I can then go ahead and stuff that in my calculator and just get a number, and that's going to give me the actual numerical value for Ka. And in this case, that is going to shake out to be 4.430, that'll do, times 10 to the power of minus 7. I've been asked for the answer to 2 sig figs, so that'll be 4.4 times 10 to the minus 7. And that's all we have to do for that one.